All right. We're actually going to introduce Hess's Law. I do have to talk to you a little bit about heats of formation too, which should be a little bit of a review, but I think I'm going to do a recorded one. I wanted to do Hess's Law with you in person because there is going to be some kids who didn't get any in the spring if they took honors this year, so I need to kind of figure out what's going on. Okay. So we're going to work on calculating heats of reactions 3 different ways. First one we already learned is that MCAT one. FYI, I am recording this lecture, so I will record it and then edit it, and then I'll post it into Google Classroom for you in the Hess's Law assignment. So the first one was our calorimetry problems, which is the change in enthalpy is equal to the mass times the specific heat capacity and the change in temperature. Next one is the enthalpy of formation. That's where you look it up in a data table, and you're going to do products minus the reactants. That's the one that I'm going to kind of do in a recorded lecture. And then this last one is Hess's Law. So let's clarify a couple things about enthalpy. So we know that the delta H stands for change in enthalpy, or really we use it interchangeably with heat because we're always doing constant pressure. So you're going to see a couple little subscripts here. Actually, there's quite a few subscripts. We're going to do a few examples of them. Enthalpy of formation is going to look like this. That's going to be where you create compounds from their elements in element form. So that's just going to have you guys understanding how elements occur in nature. For example, if I was going to do the enthalpy of formation of NaCl, NaCl is an ionic compound. Ionic compounds are always solids at room temperature. So I'm going to form this from its elements. Sodium is a metal, so it's a solid. And then I got to be careful with chlorine, right? Because when I say chlorine, I don't mean Cl. I mean Cl2. You guys know what the state of matter of chlorine is at standard conditions? It is a gas. I left myself not enough room here, like such. So this is the enthalpy of formation. Now, when I do enthalpy of formation, just like what I did with the combustion problems, I have to have a coefficient of 1 by the compound that I'm forming. So it's perfectly okay to have those fractions as a coefficient. Another one is enthalpy of combustion. Combustion is chemically reacting a substance with oxygen. So enthalpy of combustion anytime you combust a hydrocarbon, we always get the same products. What products will I get from this reaction? Carbon dioxide, which is a gas, and water, which is usually gas because there's so much energy released. So I'm going to go ahead and got to have the coefficient of 1 for this guy here, and then 5 here. You're also going to have lots of other enthalpies. So enthalpy of vaporization is going to be the amount of energy that I need to add to turn it to a gas. So the enthalpy of vaporization is always going to be positive, and we're going to take a liquid, add enthalpy of vaporization, and get a gas. You can do that with all of the states of matter. You will have a positive if it is an endothermic process. It'll be a negative if it's an exothermic reaction. So here's just a couple of them you're going to see, especially in this unit. There are some other ones that we'll touch base on throughout the rest of the year. Okay, so the enthalpy of formation is the lecture that I'm going to do as a video. Enthalpy of formation is going to be something that you look up in a chart. When you look them up in a chart, you're going to notice that the enthalpy of formation for, and this is why we do this, for any element in its standard state is going to be 0. And that's because we don't need to add energy or take energy away to get them to be like this. That's how they want to be. It is dependent on the number of moles. So here's our enthalpy of reaction. You take the products minus the reactants. So you look them up in a chart, you add together the products, and then you subtract off the reactants. And here's why. You are forming products. You are doing the opposite of forming the reactants. So remember, negative to you says opposite. And let's also talk about this. I don't like this positive minus negative and all that kind of stuff because it does get confusing for you guys. So here's our rule of thumb. We can usually avoid having to use positives and negatives if we talk about whether we have to add energy or take it away. Adding energy is endothermic positive. Taking energy away or releasing energy is negative exothermic. So in order to break bonds, and you could quote me on this because you probably learned a little bit differently in biology class. In order to break bonds, you need to add energy. So I have to add energy into a reaction to get the bonds to break. And then when we make new bonds in the products, we will get energy back. So it is endothermic to break bonds. It is exothermic when we make bonds. So here's an example of a problem. You would look these up. You multiply by the number of moles you have. Look them up in a chart. Notice elemental aluminum and elemental iron are both 0. So when you do products minus the reactants, you just got to keep track of those negative signs. Okay, let's remember Hess's law. Anybody here who was never taught Hess's law? You were never taught Hess's law? There's going to be a couple people, so don't worry, you're not going to be on your own. How about you guys at home? Anybody here never taught Hess's law?
I don't know if I was never taught it, but I don't remember being taught it.
You don't remember? Okay. So yeah, I did do the ed puzzle for you. So if that's your first experience with Hess's law, you're going to kind of have to pay a little bit closer attention to this. Like, Eli, I know you didn't take chemistry last year, right? You took it 2 years ago? Okay. So those of you who took it 2 years ago kind of had a more normal experience. But you weren't in my chemistry class that year that I was gone at the end of the year. I had to have surgery, emergency surgery.
No, you were there.
Okay. Okay, yeah, because there was 1 year too. I missed the whole month of May. So I missed tie-dye and everything. That year was just as big a disaster as this year. Okay, So Hess's law states that the change in energy of a process or a reaction is a state function. You guys remember this? We had a question about this yesterday.
Yeah.
Hess's law, and that it's a state function. I was like, oh my gosh, I'm like teaching that tomorrow. A state function is basically that regardless of the path to reach your goal, the energy to get there is constant. So there's an old proverb. There's many ways to get to the top of the mountain, but the view is always the same. So it's kind of the same thing here. So let's see an example of what a state function would be. For instance, if you want to vaporize a solid, you have two pathways. You can first take a solid, melt it to a liquid, and then vaporize the liquid to a gas. Or you can sublime the solid directly into a gas. Either path gets the desired result, and either path requires the same amount of heat energy. This is Hess's law. So here's an example of what it looks like. Remember, I told you the different enthalpies? So now you've got a couple more: enthalpy of vaporization, enthalpy of fusion, and enthalpy of sublimation. So the enthalpy of fusion and the enthalpy of vaporization, if you add those together, will equal the enthalpy of sublimation. And that's basically the concept of Hess's law. All right, let's look at the rules now. During any Hess's law calculation, there are two things that we're allowed to do to given reactions in order to manipulate the equations. You can reverse the reaction, and that makes the reactants the products and the products the reactants. If you reverse it, you're just going to flip it, then you have to change the sign of the enthalpy. So if a reaction is exothermic, the opposite or flipped reaction is going to be endothermic, basically. You can also multiply by a factor to decrease or increase the amount of reactants or products. If you multiply one thing in equation by a factor, you have to multiply it all the way through, including the enthalpy. Now, fortunately, for those of you who don't recognize seeing this, this isn't difficult, but it does take practice to not get lost in the problems. Let's see what that looked like. So let's start with a reaction. So these problems are always going to give you a target reaction. This is my target reaction. This is my end goal. And then they're going to give you some known reactions. So the reality and why this is good for us is because there's millions upon millions upon millions of possible chemical equations or reactions that we could do, and we don't know these values for all of them. So they'll give you known equations that you need to manipulate in order to get to your final target reaction. What I always do is I always start from the left and start building. If you notice, there's oxygen in each one of my known equations. So oxygen's not going to be one I focus on. I'm going to hope it falls into place on its own, which it will. So first thing I'm going to do is say I need 2 N2 gas in the reactants. So find an equation that has N2 gas. I usually label the equations 1, 2, and 3. So equation 3 has N2 gas, but it's only got one of them. So I'm going to have to multiply that by 2. Sorry, I was too happy at the clicking. When I multiply this reaction by 2, I multiply all the way across. So it'll be 2N2, 2O2 yields 4NO, and then I'm going to multiply that 181 by 2 also. The next thing I'm going to notice is equation 2, because like I said, I'm going to skip over oxygen because it's all over the place. It's going to get confusing. I need 2 N2O5 in the product side. I'm going to say, oh, I already have 2 N2O5 in the product side in the second equation, so I'm going to leave that alone. I'm going to give you a hint, guys. You're not going to get any extra equations at this point in your chemistry experience. So you're going to be given what you need, and you're going to use all of them. So the other thing I need to do is not only do I have, so now I have the things that I need in the reactant side and the things I need in the product side, but I need to get rid of the things that I don't need. For example, I have 4 NOs on the product side. So I'm going to multiply this, so I have 4 NOs on the reactant side. When you have one quantity on the reactant side and one quantity on the product side, they will cancel. I will do some example problems for you too that are a little easier to see. Okay, so here's my givens. Let's label the equations 1, 2, and 3. Then let's go down to our target equation, which we're asked to find the value for, enthalpy. That little circle up there, see how it says change in H with that little degree sign up there? That stands for standard. Anytime you see that circle up there, that means standard, meaning that it's looked up in a reference material. So the first thing I need to do is find C2H6 in the reactant side. Only one equation has C2H6, and that's the first equation. So I'm going to multiply the first equation by 2. I'm going to skip over oxygen again because you see it's in a couple different reactions, so that'll get confusing. And I'm going to say that I need 4 carbon dioxides in the product side. Well, equation 3 has 2 carbon dioxides, but they're in the reactant side, and I need them in the product. So I'm going to multiply it by 2 and flip it, which I can do, like such. Now you'll see my C2H6 is exactly how I need it in the reactants, and my carbon dioxide is exactly how I need it in the products. So the only thing I need to do now is say, well, I got to get rid of that. I've got to cancel some things, and I need some more waters on the product side. I don't have enough waters on the product side. And look at, I've got those 2 H2s there that I don't need. So I'm going to take that second equation and flip it, and that will allow me to cancel. Do you see how they cancel if one's on the reactants and one's on the products? Now look at the oxygens though. The oxygens are both in the reactant side, so they don't cancel, they actually add up. So you've got 6 O2 in one reaction and 1 O2 in the other reaction to give me the 7 that I need. And then I just add up the values.